All right. Hello. I just wanted to give you a little help with the assignment that we talked about last week about the hidden mart matrix. And I guess because of this recursion topic, I thought it would be a good idea to do a quick review of something that I usually do it in the AP class. But we did not have a chance to indulge ourselves on some more sophisticated recursive type of assignments. So if you click on the particular module link over here, which is the third one, I'm going to put a number in there. It should be 2.2.1 because it's within this. That will take us to some interesting stuff over here. Something that we did at one point, we used to do, we have done before, I should say. And I kind of do it every year. Like I said, last year was a different type of year. But if I go to the first one, it will take us to the class website for the AP class. And it talks about this interesting recursive program. The original is a little bit the actual matrix. The two-dimensional array is much bigger, but I changed it to be small so students can actually trace it and understand how recursion is actually working on this particular code, which is actually unusual. And so I wanted to spend just a little time talking about that. Not that you have to trace it, but if you're interested, it's a really good exercise in terms of understanding how recursion works and some of the terminology Professor Sedgwick used in the video. When he talks about the environment, when it comes back, and the variables, the values, I call it the scope. He calls it the environment and other words besides that. But in the end, it all turns out to be something that as you leave, think about you're going inside the room and another which is inside another room and inside another room, and you keep on doing that recursively. So every time you step out of the inner room, you're back in the outer room, and maybe that outer room doesn't have the same values that it had the inner room. Like it could be, I don't know, the most inner room was yellow, and when you step out of that room, now the color is different. It makes sense, right? Well, the variables work the same thing. So in this particular program that I want to just browse very quickly over that, because I want to give you just the idea behind how recursion can be used in this particular case, which could be very well applied for fractals. So here you have a couple of things that are taking place. For example, and I'll give you a quick rundown of what these constants are. The number 3 refers to something that you already tried, and you were there. You step into that direction. Think about this as a maze, as the name of the class calls it. And path represents the number 7, which it says, well, this might be a way to actually find the solution, to solve the maze, to find the exit. 1 represents places where you can step. 0 represents a wall. So it's kind of easy to see how the maze could be constructed with 1s and 0s, right? Or 0s and 1. Here's the tricky part. I want you to pay attention to the recursive function traverse. The recursive function traverse takes 2 arguments, the row and the column, because as you can see, this is a 2-dimensional array. Now, for the assignment, it's asking you not to use an array. The only reason why we have an array over here, a two-dimensional array here, is because we're representing, it's an abstraction of a maze. You do not need that in the matrix, the exercise for the matrix, because you're not looking for something, you're not solving a maze, you're just drawing. So you don't really need to hold on to any variable, any values. You just need to be able to, as you go, like I said before, into a room, it has a color. When you go to another room, you have a different color. And so technically you're just drawing something. But what is interesting about this is this function over here. Every time you call this recursive function traverse, you're going to have a new location, a new row, a new column. This particular variable boolean done is important to have it over here because it's always set to false unless done changes over here, unless it finds somewhere here. We're going to get there in a minute. Now, the valid function is just checking to see if you're not in any edge or a zero or a zero. So that means that it's not a zero, then I am going to actually put in there, in that location, that I already tried this path. So I'm going to change the original value, whatever that was in there, and I'm going to put it a 3. Let's say one of these ones. And if we were going to trace it, you will start with, let's see, do I have the main over here? Main search. There we go. I start with 0, 0. So it will be a 1 over here. So I'm going to change it to a 3. Well, that is, again, is irrelevant at this point in terms of the actual exercise, but it is important in terms of what comes next. So we determined that we already been there. Now, this is also checking that we didn't reach the end of the maze. And that's when we change done to true. Okay. So if we are not at the end of the maze, then we're going to start doing all these little things that this is actually the heart of this particular program, which is also, to me, is the heart of the handmade matrix. So over here, it's going to do the following. It's going to do a traverse, which is going to go down. In this case, is adding 1 to the row. That means that it's going to go down in the same column. Meaning, it's going to start from here, again, turning done to false, checking to see if the location is valid. And I'm going to put it over there, try, meaning a 3, because I step into this room, let's say. And if it's not the end of it, then I'm going to do it again. I'm going to start from the next room that I'm entering, which is again going down, as you can see. So now I'm checking, and I ended up now with a 0. So it's not a valid location when it comes over here. So it's going, what it's doing, this piece of code, is going to keep on going down at every time it enters the traverse recursive function until it cannot go any further. When it cannot go any further and it comes back to the one before. So once it got here, it couldn't go any farther down, so it's going to come back to this one right here. And what does it do when it comes back? Well, if it's not done, then it's going to go to the right. And if it's not done, and when it goes back to the right, enters again the traverse, but now it's going to start going down as long as it's valid. obviously I'm kind of simplifying the whole thing a little bit because this is just a hint, a clue, a little help for that fractal, that you could do it. I have full confidence you could do it. So it gives you an idea why you don't really need an array. This piece of code is not actually using the array to do the recursion and to actually do the fractal that you need. I'm sorry, it's not using the arrays. It's just deciding which way it's going to be going, where it has been. So I wanted to show you one more thing though. Let me see if I can get there. Yes. That's not a good, I'm not proud of it because it didn't come out as good as I wanted it to be. But this is actually the tracing of it. So if you want to look at it, you can, each of them actually you can make it bigger and it looks better, kind of. But it shows you how actually recursion is stepping through the two-dimensional array. Again, the fact that it's an array is not affecting your the original assignment that you have. The array is only there because it needs walls and it needs places to get through. Once it gets to the end, as it finds a way to continue through the maze, things are changing from, let's see, where is that? Here we go. This one. They start changing from 1s to 7s. Because 7 means that that's the path. And so here is the actual steps that is going to be taken. There is a video. Once again, I'm not very proud of it, but it does the job. I wanted to redo it, but time was never really on my side, so I did not do it. So I'm going to go back to here. This is something one student actually drew and did a presentation in class, and it shows how it actually the main thing that Traverse does, which is what you want to know for your assignment, is the fact that the recursive function is going to first try to go down. At every time that it's calling it, it will actually go down until it cannot go down any further. And then it comes back up and it's going to go to the right. But when it goes to the right, now it's going to be entering the traverse, which first recursive call is going to be to go down. I'm not sure if this is going to help you. I think it does, but it all depends on your your interpretation of how this works, and also the fact that you had to separate the array component of this example, and just think about how the actual traversing of this particular arrays is done. So you have to draw squares, and then you're going to be subdividing the squares and rearrange or aligning them as the wording goes. So if we go look at the actual wording, maybe that will help a little bit. But oh, it's 12:15. I think I'm going to finish up in 2 seconds. Here, somewhere here, it says nicely how it actually aligns the squares. It starts with a single one, and then it aligns each of one of them into 4, and then the one at the bottom right is the one that changes the color. So I did it manually up to, I think I did it up to here to really understand it. And so as one of the assignments I'm going to ask you for anybody who is doing this is to actually do the tracing for maybe one more of these, three of these squares. I'll be talking to you very soon in person. Well, through Zoom or in person. Okay, I'll see you later. 2 seconds to go.